Hello and welcome to another lectureclips.com tutorial. Today we are concerning ourselves with the topic about the moments of inertia. Now, there are different kinds of moments of inertia. There are area moments of inertia and mass moments of inertia. Here we will have a look at the area moment of inertia. Now, this is a physical quantity and it has the unit meter to the fourth power. The moment of inertia of area can be either axial or polar, and the mass moment of inertia as well. The axial area moment of inertia measures the resistance of a solid figure to bend, and the polar moment of inertia measures the resistance of a solid figure to torsion. Actually, the so-called section modulus is a measurement for the resistance of a solid figure to any kind of load, but it is connected to the area moment of inertia. Now I prepared a little example for you. Okay, this is a board or beam which rests on these 2 points here, and it is loaded with the force F. Now, in both drawings we have the exact same board and the exact same force F. And the question at hand is, in which one of the two systems will the board bend more? Well, of course, this isn't a hard question, and it is likely that most of you will have an accurate idea about it, because it is the board on the right side. The reason for this is the area moment of inertia, which is bigger in the left situation. Okay, so the resistance to bend is bigger in this system, so this one will bend more. Now, let's have a look at a simple rectangle. The axial area moment of inertia concerning the y-axis is this expression here, and the axial moment of inertia concerning the x-axis, so jx, is this integral here. Axial means concerning an axis, okay? So this means that in that case the beam will bend around the y-axis, and in that case it will try to bend around the x-axis. Imagine it like trying to rotate around the axis. Okay? I will show you what this formula with the integral actually means and how to work with it in the upcoming tutorial. For simple geometric areas, such like rectangles or triangles, the axial area moment of inertia concerning an axis that lies in the centroid should be known. Okay? So it would be a good idea for you to remember that, because you will use it a lot. Now, for a rectangle, the JYC is 8 times b to the third power over 12, and JXC is b times a to the third power over 12. And this is the axial area moment of inertia for an axis which goes through the centroid. Okay? This is very important. And you can remember it like this. Now, the JYC equals a times b to the third power over 12. Okay? We have the y-axis here, and this is a. So a is parallel to the y-axis, and it has the exponent 1, and b is perpendicular to the y-axis, and has the exponent 3. And for the JXC, it is exactly the other way around. Okay? So here we have the x-axis, b is parallel to the x-axis, so it has the exponent 1. A is perpendicular to the x-axis and has the exponent 3. Okay? You need to remember this. Okay, well, now when you think back to the board we were looking at before, we suddenly realize why it is that the board in the left situation is bent less. Because if we imagine that this rectangle here was rotated in the first system here, the bending would be around the y-axis. Okay? So the x-axis would be up here, and this would be the y-axis. Now, since the jy equals a times b to the third power over 12, and b is bigger than a, yeah, of course jy is bigger than jx. Okay, so this has a bigger value than this. Not important how big a and b is. In every case, the jy is bigger than the jx. So the bending is less here because the moment of inertia is bigger. Okay, and at the situation on the right, the bending goes around the x-axis. So this is the x-axis, and up here would be the y-axis. So in that case, the board will try to rotate around the x-axis. So this is why the jx appears and jx is smaller. And because of this, the system is more easy to bend. Alright, for a square, the axial area moment of inertia concerning an axis through the centroid is simply a to the 4th power over 12, if a is called to the side of the square. In that case, jxc equals gyc, and the same goes for the circle. And the axial area moment of inertia concerning an axis through the centroid for a circle is r to the 4th power times pi over 4. By the way, the polar moment of inertia is simply the sum of both axial moments of inertias. Okay? So, for example, for a rectangle, the polar axial moment of inertia would simply be gyc plus jxc. Alright, now we know how to calculate the moment of inertia concerning an axis through the centroid of a rectangle. But how big is the moment of inertia concerning an axis which does not run through the centroid? For example, this one here, if we would have an axis here. For this, we need the so-called Huygens-Steiner theorem. Okay, we have here the exactly same rectangle as we had before. We have the same x and y axis, and in addition to that, we now have the alpha axis and the beta axis. Now, the Steiner theorem postulates that j alpha equals jxc plus s squared times a. Please remember that formula. Now, what does it mean? So, the axial area moment of inertia concerning the alpha axis equals the moment of inertia concerning an axis through the centroid, which is parallel to the alpha axis, so this is the jxc, plus s squared, which is the distance between the two parallel axes, multiplied by the entire area of the rectangle. And it is corresponding for beta as well, so j beta is gyc plus z squared times a, and z is the distance again, the distance between the two parallel axes. Now, you always have to be careful about the sign, this sign here. It is not always positive. It is only positive when we go from an axis that runs through the centroid to another axis. Okay, so away from the centroid is plus, and to the centroid it is minus. This is very, very important. And also be aware that we are just able and allowed to use Steiner's theorem if we leave an axis through the centroid or if we are going to an axis through the centroid. It always has to be an axis that has something to do with the centroid. We're not able to use the Steiner's theorem if we go from the alpha axis to some other random axis. It always has to be an axis that runs through the centroid. Either we go or we leave it. Alright, now let's solve this equation. So, we know that j alpha is jxc, this was b times a to the 3rd power over 12, plus s squared, s is a half, times the area is ab. And we get this as a result. So, b times a to the 3rd power over 3. And now we see something interesting. If we compare this result for jy with the jxc we had here, we see it is actually exactly the same, but we just have a 3 down here instead of a 12. Okay? And this is something you can use very often, and this is saving a lot of time, and you don't need to calculate this every time. You can remember it. Every time, if we calculate the axial moment of inertia, axial area moment of inertia concerning an axis which runs along the sides of a rectangle, this side or this side, okay, it is always the same as the one concerning the parallel axis through the centroid, but just with 3 down here instead of 12, okay? We can remember this and use it in the calculations. This is because of the Steiner theorem. And we can also check the theory about the signs. Now, if we take the j alpha as a given quantity and we are looking for the jx, it would be jxc equals j alpha minus s squared times a. Okay? But now the minus s squared times a, and then we get exactly the same result. You can try it yourself. Actually, you see it here as well if you just make an equivalent transformation. Then we see that jxc equals j alpha minus s squared times a. This is because we are going to the axis that runs through the centroid, and if we're going to the centroid, it has to be a minus here. We will discuss this topic further in the next clips. See you soon.